Hello everyone, welcome back to Z Physics. Today we're going to be solving the 2019 OCR A-Level Physics Modeling Physics paper. Just a little note before we get started that these are just my solutions. They're not official exam board solutions, and please have a look at the paper in the link provided in the description from the OCR website, where you will also be able to find the official mark scheme from the exam board. Well, let's get started now with question 1. So, which set of prefixes A, B, C, or D are in the order of increasing magnitude? Well, if we have a look at A, we have micro, which is 10 to the power of minus 6, milli is 10 to the power of minus 3, centi 10 to the power of minus 2, kilo is 10 to the power of 3. So straight away we can see that question 1 has A as the correct answer. Question 2, this is an interesting one. We have a paper cone is held above the ground and dropped, then it falls vertically and reaches terminal velocity before striking the ground. Which statement correctly describes the resultant force? Well, let's have a look at what the resultant force should be. Now, before terminal velocity, the drag force will be increasing and the weight will be obviously constant and downwards. At the terminal velocity, those two vectors are equal and the resultant velocity is approaching 0 and is actually 0 at the terminal velocity. So this means that the resultant force, when we add those two vectors together, will be relatively small and pointing downwards. So it will be getting smaller and smaller until it reaches 0 at terminal velocity. Therefore, the correct answer is B, decreasing and downwards. Question 3, we have a solid cylindrical glass rod, has a length of 20 plus or minus 0.1 centimeters and a diameter of 5.00 plus or minus 0.01 millimeters. What is the percentage uncertainty in the calculated volume of this rod? Okay, well, first off, because we're calculating the volume, the formula is V is equal to L pi r squared. We don't actually need to calculate the volume in this case, we just need the percentage uncertainty. Well, because we are multiplying quantities, we add the percentage uncertainties. The percentage certainty of the length is going to be given by 0.1 over 20. Notice that I've not included the centimeters because they're just going to cancel out. For instance, I could have had 10 to the power of minus 2 here and 10 to the power of minus 2 there, but they will just cancel out. The diameter, though, is going to be squared. Another way of writing the formula for a volume is the length times pi times d over 2. The factor of a half has no percentage uncertainty, but we're squaring this. If we are raising a quantity to a power, the percentage uncertainty is given by the power multiplied by the percentage certainty in just one of those quantities. In other words, we bring this 2 down here. So the percentage certainty is no longer 0.01 over 5, it will be twice that. Don't forget to multiply that by 100, and if we put that into a calculator, we're going to get 0.9%, and the correct answer being D. Question 4, we have a simple harmonic oscillator which has a maximum speed of 24 meters per second and an amplitude of 5.6 centimeters. What is its angular frequency? The speed of a harmonic oscillator is given by plus or minus omega square root of a squared minus x squared. Now, the maximum speed occurs when we're going through the equilibrium when x is equal to 0. This means that our formula becomes V max is equal to plus or minus omega square root of a squared, which gives us just omega times a. Therefore, omega will be equal to the value of the maximum speed divided by a. Plugging in some numbers, we get 24 divided by 5.6 times 10 to the power of minus 2, which is going to give us around about 430 radians per second. Question 5, we have a car which is dripping oil at a steady rate on a straight road. The road is divided into 4 sections A, B, C, and D. Which sections of the road show the car traveling at constant speed? Well, if the car is traveling at a constant speed, then the distance between the drops should be the same, and the only one which has constant distance between, or constant spacing between the drops, is C. Therefore, that's the correct answer. Question 6, quite an interesting one. The Earth is surrounded by a gravitational field. Which of the following statements are correct for the gravitational field lines near the surface? And notice that this little section is bold. Now, near the surface, we can approximate the gravitational field lines to be parallel. There's a very, very tiny amount of curvature, which is probably completely immeasurable. So we can assume that near the surface, they are parallel. They show the direction of the force on a small mass, absolutely. For instance, if we had a small mass over here, it will experience a force straight down along the field line. And they are equally spaced because we can assume that the gravitational field does not vary significantly along the surface of the Earth. So all of these statements are actually correct, and the correct answer is D. Question 7, we have a pendulum bob is oscillating in a vacuum. This statement of vacuum just means that we don't have to consider any sort of air resistance. The maximum height of the bob of the ground is 1.3 and its minimum height is 1.1. What is the maximum speed? Well, the maximum speed occurs here, and the easiest way is to calculate the gravitational potential energy with respect to that point. Now, because the pendulum is going from 1.3 to 1.1, it's not going all the way down to the ground, the gravitational potential energy will be given by the height being 0.2 meters. So what I've done here is I've set the potential energy equal to the kinetic energy, mgh is equal to half mv squared. Notice that the masses cancel out. Rearranging for v, we get that v is equal to the square root of 2 times the acceleration times h. 2 times 9.81 times 0.2, because that's the difference in height. Square root this, and we're going to get about 2 meters per second, and the correct answer being A. Question 8. An object is falling. The weight of the object is 4.5 newtons. The wind provides a horizontal force of magnitude F on the object. We have some sort of a resultant force, which is 5.8 newtons. Well, if that's the case, we can just use simply Pythagoras, because if we add those two forces, we're going to get the 5.8 squared is going to equal F squared, which, we can even put F along here just to complete the triangle, plus 4.5 squared. Rearranging for F, we'll get that F is equal to the square root of 5.8 squared minus 4.5, let's make this a little bit more clear, squared. Plugging into a calculator, we're going to get 3.65 newtons, which leads us to a correct answer of B. Question 9, we have a solid molecular substance is supplied with energy and it starts to melt. Which of the following pairs of quantities remain the same as the substance melt? Well, kinetic energy and temperature are directly proportional to each other. When the kinetic energy of the molecules is constant, the temperature is also constant, and that always happens during melting. If you remember the change of phase curve for temperature over time, it's a step curve like this. So let's say that we have a melting phase which happens here. The temperature will remain constant, and if the temperature is remaining constant, this means that the kinetic energy will be constant. All of that inputted energy into the system goes into potential energy. So as it's melting, the potential energy of the molecules is rising, but the kinetic energy and the temperature remain constant. Therefore, the correct answer is C. Question 10. Which of the following shows the correct base units for pressure? Well, pressure is force divided by area. Force is mass times acceleration divided by area. So mass is measured in kilograms, acceleration in meters per second squared, and area in meters squared. So the overall base units, if we cancel out the m's, we're going to actually get m to the power of minus 1, because that's going to turn this into a 1. So that will be kg m to the power of minus 1 s to the power of minus 2. Therefore, the correct answer is C. Question 11, this is a really good one. So we have some data, a very much incomplete data. The student plots a graph and only 2 data points are shown. So what could that quantity y be? What could that mystery quantity be? Well, could it be the speed of the planet? Absolutely not. Remember, Kepler's second law suggests that the planets speed up when they are closer to the sun. So quantity y seems to increase the further away it is from the sun. So it will not be the speed. The planets speed up the closer they are to the sun. Let me just show you why C and D are incorrect. The gravitational potential, the formula for it, is given by minus gm over r. If that's the case, it will be trapped in the lower right-hand quadrant of the axis. So it will look something like this. And the data points should be in this negative region, so it cannot be the gravitational potential. Incredibly similar for the gravitational field strength. It has a very similar curve, and it's negative because G is equal to minus gm over r squared. So it cannot possibly be C or D, therefore it has to be B. Another way to think about it is that Kepler's third law, says that the orbital period of a planet is proportional to r squared. Now, because of that, if r increases, T should increase as well. Well, T, if we want to be really precise, should be proportional to r raised to the power of 3 over 2. But either way, in this case, when r increases, T should increase, so therefore the correct answer is B. Question 12, we have a graph showing the variation of stress and strain. What is the Young's modulus of the material? Now remember, in a stress against strain graph, the gradient is Young's modulus. If just in case you've forgotten why that is, remember Young's modulus E, it's given in your formula booklet as E, is equal to stress over strain. Rearranging for stress, we get that stress is equal to Young's modulus times the strain plus 0. Compare that with y equals mx plus c, we can clearly see that Young's modulus is the gradient. So all we need to do is take the gradient. Remember, we take a large gradient triangle, delta y over delta x. This point here is 120 times 10 to the power of 6. We'll always double, even triple check the units of the graph. They're very often, more than likely, we're going to have some non-standard units. So in this case, you have megapascal, so that's 10 to the power of 6. And at the bottom, we have 0.1%. So this is very easy to miss. It will be 0.1 over 100. Plugging into a calculator, we get 1.2 times 10 to the power of 11, and the correct answer being D. Question 13. Which column, A, B, C, or D, shows the correct sequence for the evolution of the universe between the Big Bang and the formation of the stars? So the universe does start to expand initially, quarks and leptons are formed, then hadrons, then nuclei, and then atoms. That is the correct answer, A. In general, we are going from simple to more complicated. So quarks and leptons will form hadrons, and then nuclei form, and then atoms will form. Question 14, all about the Chandrasekhar limit. So which of the following cannot be the mass of a white dwarf? Chandrasekhar's limit, which we need to remember for the exam, says that the maximum mass of a white dwarf is approximately 1.4 solar masses. Calculating 1.4 times 2.0 times 10 to the 30 gives us the maximum mass of a white dwarf star, which will be 2.8 times 10 to the power of 30. The only answer above that value is 3.2 times 10 to the 30. Therefore, the correct answer is D. Question 15, the last of the multiple choice questions. We have an astronomer analyzes the light from a distant galaxy, and we're given some wavelengths. What is the speed of this galaxy? We're going to use a good old Doppler effect. Delta lambda over lambda is equal to V over C. Rearranging for V, we're going to get that V is delta lambda over lambda multiplied by C. So it's going to be 20 divided by 590. Now remember that lambda is, in this equation, your original wavelength as measured in the laboratory. So this over here is 590. Delta lambda is the change, the shift in wavelength. If we are going from 590 to 610, then the shift will be 20 nanometers. Notice that I've not included the nanometers here and there because they will just cancel out. Of course, you can write times 10 to the power of minus 9 divided by 10 to the power of minus 9, but they will just cancel out, and we're trying to solve the multiple choice questions as fast as possible, but not too fast as well, so that we can move on to the other questions. Plugging into a calculator, we're going to get 1.02 times 10 to the power of 7 meters per second, and the correct answer being B. So question 16, explain what is meant by the ultimate tensile strength of a material. Now this is actually the maximum stress that a material can withstand prior to its breaking point. Quite a common mistake would be to write the maximum force, however that is not correct, it's the maximum stress. We need to take into account the cross-sectional area of the material. Anyhow, so let's have a look at the next one. So we have a footbridge supported by a number of metal cables, and we're given the diameter being 4.2 millimeters. We have a graph which is shown of the force and on the y-axis and the extension in millimeters on the x-axis. Describe how a suitable measuring device may have been used by the engineers to demonstrate the cable had uniform cross-section. Because the cable is quite small, 4.2 millimeters, it is worth using an accurate device, and for cables and wires we use a micrometer. Remember, we take several readings along the length of the cable and then we average. By writing down this statement, we're going to ensure that we're going to get maximum marks. So one typically goes for saying that we need to use a micrometer, and then another one to take several readings along the length of the cable and then average. I'm even going to underline this bit along the length of the cable because quite often this is missed out in answers. So next one, state any value of F when the cable behaves elastically and plastically. Now, the material behaves elastically along this first portion when the force is directly proportional to x, and this is a straight line graph. So any value of F between 0 and approximately 2 will be sufficient. So I've taken, for instance, 1 kilonewton. For a plastic behavior, when the material no longer returns to its original shape, any value from here, approximately 2 kilonewtons or so to about 2.2 kilonewtons, will also do the trick. So in this case, let's change that. There's a little mistake here. So let's just change that to 2.1 kilonewtons. Okay, next one, use figure 6.2 to determine the force constant K in Newton meters for the cable. Well, remember, in an F against X graph, the gradient is actually your force constant. So we need to make sure that we find the gradient of the graph. The rule to use is we need to make sure that our gradient triangle is large enough. In fact, I would always just use the largest possible one. In this case, this is approximately this size. This here is my gradient triangle. And once again, I'm going to be quite careful with the units. So I have kilonewtons here, I have millimeters. So the gradient will be equal to 2 times 10 to the power of 3 divided by 4 times 10 to the power of minus 3. Doing those calculations, we get that K is equal to 5.0 times 10 to the power of 5 newtons per meter. Question C, determine the breaking stress of the cable, assuming that the cross-sectional area of the cable remains constant during the test. Okay, well, we're given the breaking force, 2.2 kilonewtons. So all we need to do is calculate the area and then divide that by and then essentially do that division, and we have the answer. 2.2 times 10 to the power of 3 divided by the area, which is given by pi d over 2 squared. We're given the diameter is 4.2 millimeters. Don't forget to add in the 10 to the power of minus 3. Don't forget the brackets in your calculator, dividing it by 2 and then squaring it. If we do that correctly, we're going to get approximately 1.59 times 10 to the power of 8 pascals, which is about 1.6 times 10 to the 8. Last bit of this question, explain why the work done on the cable when the extension changes from 3 to 4 is greater compared to when the extension changes from 1 to 2. Well, the answer is quite simple. The work done is the area underneath the graph. The area is greater from 3.0 to 4.0 millimeters. A good rule of thumb to remember is that any time when we are talking about materials, if we have a graph of F against X, really almost doesn't matter what type the graph is, but the area underneath is equal to the work done. This is because the work done is in general found, for instance, if this was this triangle here, it will be a half, it will be the area, which is a half Fx. If you're doing calculus, in general, it will be the integral of the force with respect to x. However, looking at constant quantities, the work done is the area underneath the graph, and the range from 3 to 4 has a greater area underneath it. Right, on to the next question. So question 17, we have this figure which shows the variation with time t of the velocity of a ball as it falls towards the ground. Draw a tangent to the curve at t is equal to 0.25 seconds and determine the acceleration of the ball. Remember, the acceleration will be in this v against t graph, because it's not a straight line, will be given by the gradient of the tangent. So I've drawn this tangent here of that point. When we're taking the gradient, once again, it is extremely important to be using large gradient triangles, and I've used quite a large one just here. And just plugging in some values, our change in speed, it goes from 0.925, take away 0.3, and then we're going to be dividing that by the change in time, which is 0.5 seconds. When we plug that into a calculator, we're going to get approximately 1.25 meters per second squared, and because we're working up to two significant figures, I'm going to leave 1.3 meters per second squared as my final answer. So part B, calculate the resultant force acting on the ball at that time t is equal to 0.25 seconds that we've just found the acceleration of. Well, this is really handy because we could just use Newton's second law that the net force is equal to ma. Because we know the acceleration is 1.3, we can directly multiply that by the mass, which is given in the information in the question, 1.2 times 10 to the power minus 2 kg. Plugging this into a calculator, we are going to get 0.0156 newtons. Part C, use your answer to calculate the drag on the ball at the same time. Well, let's do a little diagram. We have the drag upwards and then we have the weight downwards. The resultant force will be given by W, the weight, take away the drag, because they're in opposite directions. Rearranging for the drag, we're going to get that the drag will be equal to the weight, take away the resultant force F. The weight is given by mg, and the resultant force is, well, what we've just calculated. This over here is F, of course. So 1.2 times 10 to the power minus 2 times 9.81, that's your weight. Take away 0.0156, and we're going to get about 0.10 newtons as our answer. Part D is quite interesting. So essentially we are increasing the mass of the ball. So we are inputting a little bit of sand inside of the hollow ball, or some sand. Describe how the forces acting on the sand-filled ball at a speed of 0.5 meters per second compared with the forces acting on the hollow ball. Well, there are three forces that we need to consider: the weight, the drag, and the resultant force. The weight is larger because the mass is larger. The drag, though, and this is really interesting, will be the same. I'm going to underline this because this is quite counterintuitive. The cross-sectional area is completely unchanged. The only factors the drag depends on are the cross-sectional area and the speed at which you're traveling. Because the speed remains constant and your area, your surface area, remains unchanged, then the drag force will be exactly the same. Because the force is equal to W minus D, and if the weight increases, then the resultant force will increase because the drag remains absolutely the same. So the resultant force F is going to be larger. Explain why the terminal velocity of the sand-filled ball will be greater than the terminal velocity of the hollow ball. Well, at the terminal velocity, the forces are balanced. The resultant force is 0, so your drag will be equal to the weight? Well, if your weight is larger, that means that your drag force should increase. The drag force is actually proportional to v squared, so the only way to increase the drag if your cross-sectional area remains the same is to be moving at a higher speed. So therefore the terminal velocity will be larger. So question 18 about simple harmonic motion. Part A is asking us to use the defining equation for simple harmonic motion to show that the natural frequency is about 1.4 Hertz. Well, the defining equation is that the acceleration is proportional to the displacement. A is equal to minus omega squared times x. Because we're looking at the magnitude, I have ignored the minus sign and just said that A is equal to 2 pi f squared, because omega is 2 pi f multiplied by x. When we square the symbols out, we're going to get A is equal to 4 pi squared f squared times x. Rearranging for f squared, we get that f squared is A over 4 pi squared times x. Square rooting this and inputting some numbers. Remember, the acceleration is given as 3.6 and the displacement x is 4.6 times 10 to the power of minus 2. Carefully inputting this into a calculator, we're going to get approximately 1.4 Hertz. Part 2, this is an interesting one, calculate the amplitude of the oscillations. Now, because we are starting at maximum displacement, we are going to be using the cosine equation. There are two equations that we can use. We could either use x equal to a sine omega t, but we only use that if our problem starts at the equilibrium position. Here we're starting from a fully extended position, so x will be a cosine omega t. Notice that this equation gives us the displacement at time t. This lowercase t is not the time period. So in fact, let me just write this down. This equation gives us the extension x at time t. The time that we are given in this case is 6.5 seconds. So t is already given. So we're looking for time for the displacement at the time t is equal to 6.5 seconds. Well, because omega is 2 pi f, x will be a cosine 2 pi f times t, and we're actually given everything in this equation but the amplitude, so we can directly rearrange it. We know that x is 4.6 times 10 to the power minus 2, given in the previous part of the question, and we take the cosine of 2 pi times the frequency, which we've just found to be 1.4, times the time, 6.5, and if we plug that into a calculator, we're going to get approximately 0.057 up to 3 significant figures. Part B, this is a really interesting one. So we have the spring system is now made to oscillate in air. There are different types of energies are involved. Describe the energy changes that would take place as the mass moves from the lowest position in its motion through the equilibrium position to the highest point in its motion. There are many different ways of structuring this question. I think that probably the easiest way would be just to think about all the different types of energies which are involved in this motion, and then comment on each of them. For instance, GPE, that's an easy one. It's a minimum at the lowest point, and then it just increases as the mass goes upwards. Elastic potential energy is at a maximum at the lowest point, because then you're fully extended. It is 0 at the equilibrium when x is equal to 0, and it's maximum at the maximum height at full extension. Kinetic energy is going to do the opposite. It's going to be 0 at the lowest point, and it will be 0 at the highest point as well, but would be a maximum at the equilibrium. All in all, the total energy will be decreasing due to air resistance, and the amplitude of the oscillation will be slowly decreasing. Part C, we have this figure showing the mass in the spring now attached to a mechanical vibrator which can oscillate with a variable frequency. So we're given that the frequency is varied from 0 to 2.5 Hertz. Sketch a graph to show the variation with the frequency of the amplitude, and we're going to label our graph K. this is our resonance curve, which is going to peak at the natural frequency. We calculated in the very first part of the question, the natural frequency is 1.4 Hertz. So the graph is going to be increasing, reaching a peak, only a single peak at 1.4 Hertz, which I've labeled down here, and then it will be decreasing like so. For the next part, if we were to add in some damping, there are two things that happen. Number one, the amplitude will be decreasing at all points, and we can see that as the curve, which has been labeled D, is underneath the first curve. The second part is that the peak gets shifted a little bit earlier, so the whole graph gets shifted a little bit to the left, or the peak gets shifted a little bit to the left. Explain why the phenomenon demonstrated in this experiment, which is resonance, can cause problems for the engineers. Well, when we're describing resonance, this statement is going to be invaluable in gaining a mark. If the driving frequency matches the natural frequency, resonance occurs. That is the condition for resonance. The driving frequency matches the natural frequency. When that happens, the amplitude increases, which can lead to damage. Question 19, we have a car which is traveling along a straight road at 18 meters per second. The driver sees an obstacle and after 0.5 seconds applies the brakes. Well, we're given the stopping distance that's been highlighted, and then we need to find the magnitude of the deceleration of the car. What we really need though is the braking distance. So our thinking distance is going to be 18 times 0.5, which is 9 meters. Notice the little tiny mistake here. This shouldn't say stopping distance, this should just say braking distance. So let's just correct that. This is our braking distance, and this of course is our stopping distance. Take away the thinking distance, which will be 29 meters. After we have the braking distance, we can use the good old v squared is equal to u squared plus 2as to work out the acceleration. Because the car is stopping, our final speed is going to be 0, and our initial speed will be 18, and we know that s will be 29, so we can directly rearrange for the acceleration. That's going to be minus 18 squared divided by 2 times 2 times 29. Plugging this to a calculator, we're going to get minus 5.6 meters per second squared. Okay, now let's have a look at this 6 marker. We have a student that rolls a marble at different speeds on a carpet to model the braking of a car. We want to investigate the relationship between the distance traveled x and its initial speed v. So the speed v and x are related by the equation of half mv squared. That's the kinetic energy is equal to fx, which is going to be the work done by the frictional force. Describe how an experiment can be conducted and explain how the data can be analyzed. Even before starting to do this question, we know that we're going to be plotting a graph and we're going to be finding f using the gradient. Well, let's first off describe the experiment. How are we going to do it? The easiest way would be to roll the marble at different speeds. For instance, we could use an inclined plane and just vary by how much it is inclined. Then we could place some light gates over here. So let's say that we have some light gates, and this over here is our marble, which is going to be rolling down the hill. Now, as soon as it reaches the horizontal part, we could find the initial speed v using the light gates. We could vary the initial speed v by just varying the angle of the incline. For instance, if we do that, the speed is going to be lower. If we do that, the speed is going to be really, really high. So I've said over here, roll the marble at different speeds by using an inclined plane at different angles. We're going to measure the speed v using light gates at the end of the inclined plane. This is by far the most accurate way, and light gates are a pretty standard way of measuring speed. So in 6 markers, if we need to measure speed, we're always going to be using light gates. We're going to measure x with a ruler, but we're going to do that multiple times and average. So we want to be absolutely sure that we get the right answer. So let's say that the ball stops here and this over here is our x. We're going to use a ruler and we're going to be measuring this multiple times. Additionally, we're going to be measuring the mass with a top pan balance. We're going to vary v, and then we're going to see how that affects the distance x. In terms of the explanation, for instance, we could plot a graph of v squared against x, because a half mv squared is equal to f times x. Just rearranging for v squared, we're going to get that v squared is equal to 2f divided by m times x. I mean, we could compare this with the equation of a straight line where y is equal to mx plus c. Please don't confuse m the gradient with m the mass. I've called it just gradient later on. And if v squared is on the y-axis, if x is on the x-axis, we should get a straight line for the origin. And this over here, 2f over m, will be our gradient. So this is a very important statement to remember for 6-mark question. If the graph is a straight line for the origin, v squared, or whatever is on the y-axis, will be proportional to x, whichever quantity is on the x-axis. I've also said that we're going to plot a line of best fit, and the gradient is going to equal to 2f over m. The final step is really important, which tells us exactly how to calculate the force F, which is going to be, just rearranging for that, it will be m times the gradient divided by 2. Notice that there will be multiple other options for, or at least a few other options for a graph. For instance, we could have plotted a graph of x against v squared, in which case our gradient will be the inverse. But hopefully this helps. Right, on to the next question. So question 20, we have a graph of the force acting on a decelerating bicycle against the time t. The first part is asking us to use Newton's second law of motion to explain the physical quantity represented by the area shown underneath the graph. Now, Newton's second law says that the net force acting on an object is proportional to the rate of change of momentum. In other words, F is equal to delta P divided by delta T. Now, just rearranging for the change of momentum, delta T, then we're going to get that our impulse, which is F delta T, is equal to the change of momentum. Because this is a force against time graph, the area underneath the graph is the impulse, and that is equal to the change in momentum. Part B, so use the figure to calculate the initial speed if the mass of the cyclist is 71 kilograms. Because our impulse is equal to the change of momentum, our area is also equal to the change of momentum. Using a large triangle, so I've used 900 and 2, so I've used this whole triangle over here. I'm going to get that the area is a half base times height, so it's going to be a half times 900 times 2, and that's going to be equal to the change of momentum. The final speed is equal to 0 because the cyclist is stopping. So rearranging for mu, we're going to get that mu is 900 over 71. It should really be minus 900 over 71. However, they're asking us for the initial speed, so therefore I've just taken the magnitude, which is about 12.7. So overall, that is going to give us 13 meters per second. Part C. Complete the following figure to show the variation of the speed of the bicycle from t is equal to 0 to t is equal to 2 seconds. Well, the force during this time is decreasing. You can see that in the graph above. If the force is decreasing from t is equal to 0 to t is equal to 2 seconds, then the acceleration will also be decreasing. I mean, remember, that's the case because F is equal to ma, and if the acceleration is decreasing because the force is decreasing, well, the gradient of this line, the gradient of the tangent of this line will also be decreasing. So the graph will be decreasing, but it will also be tending towards a flatter curve. The gradient of the tangent will be going down and down, so becoming more and more flat. Question 21, we have a substance and we're given the graph of the temperature against time. Use the kinetic theory of matter to describe the solid phase, which is section AB, and the liquid phase, which is CD. Well, let's start off with the solid. The molecules in a solid are arranged in a fixed lattice, and the particles are vibrating around those fixed points. They're actually performing simple harmonic motion. The amplitude of vibration increases from A to B as the temperature increases. In terms of the liquid region, which is from C to D, the particles are a little bit more further apart and they vibrate but no longer around fixed points. In fact, the liquid no longer has a regular structure of the arrangement of the particles. Additionally, the particles can now flow past each other, which wasn't the case when we were talking about the solid. Now, the next one is really interesting. Use the figure 21 to explain how the specific heat capacity of the liquid compares with the specific heat capacity of the solid. Before you have a look at my solution, have a look at this. So it's clear that the liquid section has a higher gradient. Now, what does that tell us about the specific heat capacity? Because E is equal to mc delta theta, we're going to use our typical trick by dividing by delta T. So if we divide by time, let's add a little delta over here, what we're getting is the power on the left hand side and change in temperature divided by change in time. Well, hang on a minute, this is actually the gradient in a temperature against time graph. So what we get is that the power is going to equal mc, the specific heat capacity, times the gradient. I've called the gradient just grad, just so that it's not confused with m, the mass. Rearranging for the specific heat capacity, we get that C is going to equal P divided by M times the gradient. Now, if the gradient is higher, if it's steeper, as it is the case for the liquid, then the specific heat capacity is going to be lower. Therefore, the liquid has a greater gradient, that region, and therefore a lower specific heat capacity. The next one is a typical definition. State what is meant by the internal energy of a substance. That is the sum of the average distributions of the kinetic and potential energies of the particles in a substance. Quite a typical mistake would be to forget this statement of the particles or the molecules. You could also say that, but you need to mention that it's the sum of the average distributions of the kinetic and potential energies of the particles themselves in a substance. Now, the next one is kind of interesting. Beyond the point E in figure 20.1, the substance behaves as an ideal gas. Now, an ideal gas has no potential energy, so it only has kinetic energy. The potential energy of an ideal gas is assumed to be 0. The mass of a gas molecule is 4.8 times 10 to the power minus 26. Calculate the root mean square speed of the gas molecules at a temperature at 250 degrees. In order to do that, we're going to use the formula half mc squared, where c is the root mean square speed, is equal to 3/2 kt, where k is Boltzmann's constant. Rearranging for the RMS speed squared, we find that this is equal to 3 kt divided by m. The halves are essentially going to cancel out. Then we square root that expression. So this is going to equal to 3 times 1.38 times 10 to the power minus 23. This here is Boltzmann's constant. T here, though, is given with the symbol, well, T. This means that we will need to convert this temperature from 250 degrees to 523, which is the temperature in Kelvin. That's why I've put in 523 for the temperature, divided by 4.8 times 10 to the power minus 26, which is just this quantity here, the mass. When we put that into a calculator, we're going to find that this is approximately equal to 671 meters per second. In this case, we are using two significant figures, so I've left the answer out as 670. Part 2 is really interesting. Calculate the internal energy of 1.3 moles of gas at 250 degrees C, which is once again equal to 523 Kelvin. I'm going to write this down over here. Okay, well, first off, we need to know how many particles there are in 1.3 moles. Well, because each mole is an Avogadro's number of particles, 6.02 times 10 to the power 23, what we actually have is 7.826 times 10 to the power 23 particles. We know the kinetic energy, the kinetic energy at a given temperature, for instance, at 250 degrees. We could use the kinetic energy is equal to 3/2 kt to figure out the energy for one particle. Doing that, we find that 3/2 times 1.38 times 10 to the power minus 23 times the temperature in Kelvin will give us 1.08 times 10 to the power minus 20 joules for one particle. So one particle has this much kinetic energy, and that's the entire internal energy of that particle because it has no potential energy because it's part of an ideal gas. So if this is the energy for one particle, if we multiply that by 7.826 times 10 to the power of 23, we are going to get 84,000 or 8,452 joules, which is the correct answer. So for question 22, this is essentially a torque question. So we have a screw over here and we have two forces, 350 newtons acting this way, 350 newtons acting this way. To calculate the magnitude of the torque, remember the torque is given by the magnitude of one of those forces that create a torque couple multiplied by the perpendicular distance between them, which is 5 times 10 to the power minus 3. Plugging that into a calculator, we are going to get 1.8 newtons. The next one is a little moments question. We have a wooden sign which is hung up on the screw at a point A, and the forces acting on the screw are shown in the figure. We're given the fact that the inside section of the wall exerts a maximum downward force of 31 newtons at a certain distance from the outer edge of the wall, and we're given some distances as well. We're going to need to use the principle of moments to calculate the maximum mass of the wooden sign. Let's do this. Let's think about some of the moments involved in this problem. So this force F here is going to force the screw to move or to rotate in the clockwise direction. So this moment here will be clockwise moment. The 31 Newton force will force the screw to rotate in the anti-clockwise direction, so this here will be an anti-clockwise moment, assuming that the pivot is right here, which I've labeled as the point P. Now the force R will exert no moments actually, so no moments. The reason for that is because the force R is acting on the pivot, so it acts on the pivot. Another way to think about it is a moment is force times distance, so it's going to be R times the perpendicular distance to the pivot, which is 0, so the moment of that force is going to be 0. Now let's use the principle of moments. So the principle of moments says that the sum of the clockwise moments is equal to the sum of the anti-clockwise moments for an object to be in equilibrium. The clockwise moment of F is going to be given by the force F times its distance to the pivot, which is 7.0 times 10 to the power of minus 3, and the 31 Newton force has a distance of 3.0 times 10 to the power of minus 2. Rearranging for F, we're going to find that the force is about 132 Newton. Check. Once we have the force, this is the downward force, of course, just simply from the mass. What we need to do is essentially convert that force to a mass. So we need to divide that by mg. So because the force is equal to mg, then the mass, of course, will be equal to 132 divided by g, which is 9.81. And if we do that, we are going to get approximately 13.4. Let's leave that as 13.5 kilograms. Okay guys, so let's have a look at this really interesting 6-marker question, which is based on some real astrophysics data. So we have a table full of some very interesting data. We're comparing two stars called TRAPPIST-1 and our Sun. We're given the two luminosities, we're given the surface temperature, the radius of the star, which we probably have to calculate, the distance between the Earth and the Sun, and respectively the distance between the planets and the star TRAPPIST-1. We're also given a new formula. And quite often in 6-marker questions they might give us a formula which we've not seen before, which is not on the spec, but it will be one which is pretty simple to deal with, such as in this case. So the temperature T in Kelvin of the planet, its distance from the star, and the luminosity L are related by the following expression. So this is for all planets. T to the power of 4 d squared divided by L is equal to a constant. So first question is asking us the average temperature of the Earth is about 290 Kelvin. Explain how life may be possible on some of the planets orbiting TRAPPIST-1 and support your answer by calculations? Well, first off, even though TRAPPIST-1 is cooler than the Sun, the orbiting planets are considerably closer. It may be possible for the temperature to be comparable to the temperature of the Earth. Now let's calculate this. First off, we can calculate directly this constant as applied for the Earth. We know that the surface temperature of the Earth on average is about 290 Kelvin. So we raise that to a power of 4, we times that by the distance from the Earth to the Sun, which is 1.5 times 10 to the power of 11. We don't forget to square that. We divide that by the luminosity of the Sun, 3.8 times 10 to the power 26, and we're going to get a value for that constant, 4.19 times 10 to the power of 5. Now this will allow us to calculate the temperature for the various planets on the TRAPPIST-1 system, because we can use the same equation, T to the power of 4 d squared divided by L is equal to 4.19 times 10 to the power of 5, because this constant will be the same for the two planets. We're given the luminosity of TRAPPIST-1, we were looking for the temperature, and we're given two distances. So we're given the distance can vary between 1.6 and 9 times 10 to the power of 9. Now because of that, we can actually calculate two different values for a maximum temperature and a minimum temperature. The planets which are closest to TRAPPIST-1 are going to have the highest temperature, and the planets which are furthest away are going to have the minimum temperature. Just rearranging the following equation, T4 d squared divided by L is equal to the constant. Let's rearrange that for the temperature. T to the power of 4 is equal to 4.19 times 10 to the power of 5 multiplied by L divided by d squared. Now when we substitute, I'm going to make sure that we calculate the maximum and the minimum values. The maximum is given when the distance is the smallest, i.e. 1.6 times 10 to the power of 9 squared. So plugging this expression into a calculator, we're going to find that the maximum temperature is about 425 Kelvin, which corresponds to about 430 Kelvin when written down in two significant figures. And because all our data is given up to 2 sig figs, I'm going to be using that. The minimum temperature is using exactly the same expression. However, rather than 1.6 times 10 to the 9 for the distance, I have given the maximum distance, which is 9.0 times 10 to the 9, and we're given that the minimum temperature is about 180 Kelvin. Well, look at that. The maximum temperature is 430 if we're really close to the planet. The minimum temperature is about 180 if we're pretty far away from the planet. So this means that there may be a planet in between somewhere with a temperature very similar to the temperature of the Earth. We have answered we explained the first question, how life may be possible. We have also supported our answer with calculations. There's only one bit which we haven't answered fully in this question. That is to use our knowledge of luminosity to show that the radius r of TRAPPIST-1 is smaller than the Sun. As we know, luminosity is given by the following expression: Stefan Boltzmann's constant multiplied by 4 pi r squared times t to the power of 4. Rearranging for r, we're going to find that r is going to equal the square root of L divided by Stefan's constant multiplied by 4 pi times t to the power of 4. So our luminosity is 2.0 times 10 to the power of 3. Stefan's constant is 5.67 times 10 to the power of minus 8 times 4 pi times 2,500 raised to the power of 4. Quite a typical mistake would be to forget that power or to square it instead. So plugging this into a calculator, we're going to find 8.5 times 10 to the power of 7 meters, which is smaller than the value for the Sun. And we have now fully answered this question. So part B, which is all about Kepler's third law. The first question is pretty easy. This equation is actually given in your formula booklet. So Kepler's third law, as long as we can recognize it, t squared is proportional to r cubed. The second question is all about the application of this equation below. So in fact, if we come across a question straight after we've just been asked to write down an equation, chances are in more than 90% of the cases that we'll have to use this exact equation. So let's apply Kepler's third law to estimate the height of a geostationary satellite. First off, the time period t will be equal to 24 hours. Well, let's convert that to seconds really quickly. So it's going to be 24 times 3,600, which is going to give us 86,400 400 seconds. So we can then directly apply Kepler's third law. T squared is equal to 4 pi squared over gm r cubed. Now, in this case, we know what T is, we know what 4 pi is, we know what G is, and we're given the mass of the Earth, so we can directly rearrange for R. Rearranging for r cubed first, we get that r cubed is gmt squared, don't forget the square, really, really important, divided by 4 pi squared. So r will be the cube root of 4 gmt squared divided by 4 pi squared. Rearranging for r really carefully and putting into this equation into the calculator, we're going to find the cube root, not the square root, of 6.67 times 10 to the power minus 11, that's g, multiplied by the mass of the Earth, multiplied by the orbital period t squared. We're going to divide this by 4 pi squared. And if we do this correctly, we're going to get 4.23 times 10 to the power of 7 meters. Moving on, this next parallax question is really, really interesting. So this is essentially the way how astronomers estimate the distances using parallax angles. So we're given the position of Proxima Centauri and then another picture of the position of Proxima Centauri against the fixed background 6 months later. And we're given a scale. Now, if we were to measure this, because we're given a scale, we can actually use a ruler to measure this. In this particular scale, 2 centimeters is equal to 1 arc second. So the distance that is measured from here to here using a ruler, which I can't show you because I'm using my digital whiteboard, is 3.1 centimeters. So using the scale, this 3.1 centimeters is going to correspond to half of that in arc seconds, because 2 centimeters is 1 arc second. Therefore, the distance here will be 3.1 over 2, so this whole thing will be 1.55 arc seconds. But this is not the parallax angle. Remember, the parallax is given by essentially half that value, because if the Earth, let's say the Earth is here, the Sun is there, then we take 2 positions, then the parallax angle is going to be given by half that. So what we need to do is divide that angle by another factor of 2 to get the parallax angle. So it's going to be 1.55 divided by 2, which is going to give us 0.78 arc seconds, which is about 0.0 arc seconds with as it has been requested or required by the question. If you're a little bit unsure about parallaxes, I'm going to leave a link in the description on my parallax video in which I explain those in great detail. Right, moving on, use your answer to calculate the distance of Proxima Centauri from Earth in light years. We're going to use the d is equal to 1 over p equation. However, please note that in this equation only works if d is in parsecs and p is in arc seconds. This is the only units that this equation works in. So d is equal to 1 over p, 1 over 0.78 is going to give us 1.28 parsecs. We're given that 1 parsec is 3.26 light years, so multiplying that by 3.26, we're going to get about 4.17 light years, and 4.17 light years is about 4.2 light years. This next question is really, really interesting. So we have a model of the galaxies in the universe, and they may be assumed to be distributed uniformly through space. So each galaxy has about 10 to the power of 11 stars, absolutely mind-boggling number, and the mass of an average star is similar to that of the mass of the Sun, about 2.0 times 10 to the power of 30 kilograms. Well, we can actually estimate the gravitational force between 2 neighboring galaxies. What we're going to use is F is equal to gmm over r squared. I'm just using the magnitude, so I've not included the negative sign here, taking account into the direction of the force. Now the distance between 2 neighboring galaxies is already given, so this over here is our distance r, and our mass is between the 2 neighboring galaxies will be the same, and we can estimate that using this information. So F is equal to gmm over r squared. G is 6.67 times 10 to the power of minus 11. Now the mass of a single galaxy will be given by the mass of one star, 2 times 10 to the 30, times the number of stars, which is 10 to the power of 11. Because the two m's are now equal, I've actually squared this number and I've divided that by the distance squared. Very, very typical mistake here would be to forget to square either one of those quantities. Most often it's the r that people usually forget to square, but I'm doing a little check anytime there's a square in the equation. Okay, I've not forgotten to square this, and when we've plugged this in, we're going to get about 1.36 times 10 to the power of 26 newtons for the force. Part 2 showed that the mean density of the universe is about 7 times 10 to the power of minus 29. Well, density is mass over volume. So if our mass, we estimate it to be 2.0 times 10 to the 30, the mass of one star times the number of stars, and then we're given that the volume of each cube is 2.7 times 10 to the power of 69. Don't try and calculate this because this information is actually given in the question already, 2.7 times 10 to the power of 69. When we divide those two numbers, we get 7.4, which is about 7 times 10 to the power of minus 29 kilograms per cubic meter. So most of the universe is actually seems to be empty space. Now, why does the actual mean density of the universe be different from the value that we just calculated above? Two main reasons come to mind. The first one is that the universe is actually expanding constantly due to dark energy, and that's not been taken into account at all. The equation or the question above assumes that the universe is static, which is not the case. Second of all, there may be dark matter not taken into account. In fact, there most likely is a considerable amount of dark matter that we have not taken into account into this equation. Okay guys, well this was quite a long video, but we have finished the 2019 paper. Well done for doing this paper. Good luck in your revision, and if there are any questions about this paper, do get in touch. Thank you very much for watching, and I will see you in the next video.